right, let's go ahead and get started. How's everybody doing? Good. Good. I haven't seen you in a while. I'm sorry. Your exams should all be uploaded now, finally. I'm also sorry about that. I ended up with I usually have a very fast scanner that just pulls things through, and instead I had like this all-in-one, and I was just like feeding them one by one. So time well spent. But if you, for any reason, like didn't get your exam posted on Canvas, or if it's not readable or something, let me know, and I can fix it. Overall, people did well on the exam. I know a few people probably didn't do as well as they wanted to do. That's okay. Don't get too nervous at this point about that. One thing about this first exam is that, one question might be worth 10 points, and that can really hurt, even if you make a simple mistake. So the next two exams have a little more opportunity to have smaller point items, which I think is better. But the constraint is we have to fit it in 50 minutes. So, yes.
When you said that, the final exam is optional, and it replace the lowest test grade or something like that too?
Yeah. Yeah, so you don't have to take it, but if you do take the final and you do better than any of your other exam grades, then it'll replace one of those. And if you do worse, it doesn't count for anything, so it can't hurt you.
And my next question is, what is the process of what's going to happen with this demo? Like, we write any linked list we want, displaying whatever we want, and when we get in there, he asks us to turn it to the linked list. Do we go home and do that, or do we do it right there?
You do it right there. Yeah. So on the demo, we have some code on Canvas that is the doubly linked list that we wrote in class. So what you may want to do is take that, convert it to a singly linked list, and then you go in with the singly linked list code, and then you'll write the part that makes it double.
If we wanted to, we could write any type of singly linked list and then just convert it to a double linked list?
Yeah, you could, and it needs to be, the data type needs to be a string instead of an integer, I believe. Let me make sure. So, all right.
I didn't read anything about being a string.
For the tests on the next page, it has to be a string.
Does it have it on the, okay, yeah, there we go. Thank you. Yeah, so you can see like the inputs here are strings.
Wait, so what's that?
So if you remember in our code that we wrote, like the data was always just a number, just an integer. So instead of an integer, you'll need to make it a string. Yes?
One thing I was confused about is for the display on this testing, it has display and then cout in the parentheses. But the one that we wrote just automatically.
It just has the, yeah, okay. That's a good point. I think the one that the TA is using takes in an output stream. I will update that for you on Canvas so that you can take cout as a parameter rather than the way we were doing it, we're just printing it. I will add that after class so that you can see that way of doing it. I'm not sure that it's important, but yeah, because of this example code, the TAs may be expecting that, and so it's not a big deal. It's just a little bit of syntax, but I will add that after class so that you don't have to worry about that part of it.
So we got to use, what is this exactly? The example testing code, we got to use those words or something?
Yeah, so this is like in your main method, you'll want to be able to do this. So like in this case, they've created a linked list named LL, and they're calling append, they're calling display, remove, tail display, tail remove, all of the functions that are part of the linked list. And so you'll want to be able to run this for the TA. And so it's just to show you like what the output should be, right? So like if you have this input in your main function, and you run it, you should get this as your output.
This might be a really bad question.
Yeah,
I
yeah,
already
yeah.
know. But I thought that when we made our display function, it had no input. We have.
You have the C out, right? Yeah. So let me update that for you because yeah, I didn't realize that they were still doing that here. But it is so. What you can do is you can pass in C out as a parameter and then use that as an output stream. It's not particularly important. It's C++ specific kind of thing. I will get that up there right after the class so that you all have it. I apologize for not seeing that sooner.
And that's my bad. I don't know much about much. I've never seen it before. It was.
Yeah, no, it's like kind of a fun thing to just jump out of nowhere. But yeah, I will add that in for you. Let me see if there's anything else.
But I shouldn't be worried about the fact that I've never seen it before.
No, you shouldn't be worried about that at all. That's just something that we haven't used and that the assignment, the programming challenge used previously. And I think that, so we update them every, semester, and it wasn't clear if that was going to be part of it or not, but it is, and I'll add that for you. Other questions about the programming challenge? Okay.
I mean, a lot of the code that you have for the double linked list, I could comment out to make it saying did I delete the semicolon or delete the slashes in front of the TA?
No. So yeah, that's a good idea. But no, you've got to go in without the code there completely, and then write it. Yeah. Yeah. And so I think if you go through the process of converting the doubly linked into the singly linked, that'll help you know exactly what is being taken out, so you can put it back in. And the TAs are very reasonable with you, so that if it's like a small thing or something that's tripping you up, they will work with you as much as possible. And of course, if it just gets to where you can't get it done, you can come back and do it. And usually they're very very good about getting you in quickly to do that. Okay.
The last thing I have is there a time frame that I'm expected to get this all done? I don't
Once
wanna,
you're there?
Yeah, I don't want to sit there for 20 minutes and be wasting a lot of their time.
Yeah, so I think it's they try to hit try to do 5 minutes, 10 minutes at max. I mean, and there's some flexibility, right? Like if you're, they're not going to cut you off because you're typing a little bit slow or something, But if you're having, if you really don't know what's going on and you're just I'm just going to brute force and try every possible thing, then they're going to be like, I'll just come back, later. Yeah. Okay. So, course logistics. We are here. And we're going to do trees, a little bit of trees today, and then we're going to do more trees on Friday, and then your challenge one is also due on Friday. So also just be sure you've signed up for a demo slot if you have not done that. That link is on Canvas. Also, wanted to remind you about this. So one of the reasons that you've had your class canceled more times than I've ever canceled class is because we've been working on this play that's being put on one more time tonight in Lee Hall. So if at 6 p.m. you don't have anything to do and you would like to see a comedy that has humans and robots acting together, I saw at least one of you there last night. Yes?
By robots, you mean you actually have something automated there?
Mm-hmm. Yeah.
Oh, wow.
Yeah, so several robots too in the show, and so it's pretty fun. We've been my lab has done the robotics side of it, and we've worked on it since January. It's been really fun. It's been a lot of work. And of course, we have in this case, it's the Honors College students who are the actors, and they're great too. And the show is pretty funny. So it is interesting. Definitely something worth seeing. And it should be fun since it's the last performance. We kind of might do more fun things. But yes, that's where I've been, and that's been kind of stealing a bit of time, but that is now wrapping up, and so I will be back here doing data structures hardcore with you all. Exam 1 notes, again, pretty much everybody did very well. I will get you I will take a look at like the question by question to see what was missed the most, and if there's anything that was easily confused. I know a few of you have emailed me things about this. I will get back to you very soon. I do apologize. Again, this play thing has kind of taken a lot of time this week. But yes, I have your emails, and I will get back to you on that. There weren't any questions or anything that jumped out as being like that needed to be excluded because like everyone missed it or it had some confusion within it. But I will get you a breakdown of kind of what things were the most difficult and how everybody did on that. Okay. So today I just want to talk a little bit about trees. It's a new data structure for us. So thinking about the data structures that we do know so far, of course we've got arrays, vectors, lists, dictionaries. We all kind of came into this course knowing about those things and being very familiar with them. In this course so far, we've looked at linked lists, we've looked at stacks, queues. And what do these have in common, kind of? Yes.
They're all linear.
Yes, that's the perfect answer. Yeah, they are. They are all linear. So you might say they're kind of like a line or a chain, linear-ish, and we'll definitely call them linear. And all that means is that in general, we start, like if we're going to look at one of these collections, we have to pick a point where we enter, and then we move through the data structure one node at a time. And so usually we can only either move in one or two directions, right? Maybe we move forward down a list or we move backwards down a list. And that's what we've covered so far. That's probably a good chunk of like practical use of these concepts in the world in programming and implementations. These are go-to things, right? Arrays, lists, dictionaries. These are things that we need all the time. So can we make something that is non-linear? Yes, we can. So ideas on that.
More than one node connects to each other.
Yeah, so multiple connection points per node, right? So apart from trees, may have been a bit of a spoiler. Can anybody think of other data structures that?
Maps, graphs.
Graphs, yeah. So graphs are. We'll talk about trees, and trees are just a subset of actual graphs where you can have lots of connections going on. And we'll look at a few more of them as the semester goes. So with trees, we're going to spend some time, today we'll talk about the structure in general, the basic ideas, kind of just the very simple things we need to orient. And then we'll start to look at what they're useful for, why we would want to do this. And then we'll start to look at the actual algorithms that go with the structure and how they are used and what they're used for, how we can make things more efficient using a structure like this. So like we've talked about finding something in any of our linear data structures, we typically have to kind of scan through things if we don't have a specific order or a scheme going on. With these nonlinear data structures, we can kind of make paths through the data structures that give us an advantage when we want to do specific things. And so, yes, trees. This was beautifully generated by Adobe Firefly and then rendered in green by this Epson projector. So that is a more artistic version of a tree. And then this is a more straightforward version of kind of something practical that we see trees used for, right? So like a big one is just mapping out like relationships between people, you know, who's the parent of this person, who's their child, who is their sibling, things like that. That's a very practical example of a tree. Can we think of other examples of trees? Tree-like structures.
Like in general?
Yeah,
In
just,
life?
sure.
I don't know, the animal kingdom?
Yeah, okay, great, right? Like, so you want to do like a taxonomy of, you know, different animals, or maybe even like within a group of, you know, a certain species or something, you want to further categorize and link and make hierarchies of these things, right? Yeah, tree is definitely a way to do that. And I don't remember like the whole kingdom, phylum, or whatever. It's actually changed since I was in school. But, you know, you can think of like anything with a hierarchy, right?
A corporation with multiple locations?
Perfect, yeah. Corporations, definitely. So you've got to organize, like, you know, you've got like the corporate structure, you've got regional branches, you've got, you know, your local branch, anything like that. What about in kind of more computer world, things that we use?
A network?
Network, yeah, network's a great one. So you can, and a network, it definitely fits in a tree in a lot of cases. You may think of it more as a graph later because it needs to be a little bit more connected at times. One that's probably you don't think of because you use it so much is the file system on the computer, right? So you kind of have like a root level and then, you know, you just nest in. So there are definitely a ton of examples of this tree-like structure, whether it's, you know, in an actual like application out in the world, or if it's something just kind of more direct that we're using to program or to organize data. So, kind of talking about this with a little more terminology. The idea of the tree is that we're able to capture these relationships between pieces of data, and in our case, we'll call them nodes, as we call everything nodes. And we're able to capture this hierarchy. And so just like with a linked list or a stack or a queue, each node in that tree will have some data that it holds. If you were thinking of like a family tree, you know, it might be the person's name or something like that. But it will also have usually 2 or more links to other nodes in the tree. And so you'll usually have a link that is, like if you're a parent, you may have links to your children, and however many children you have, you know, you have that many links out to them as nodes. And so these are actually called children of the node. So the terminology kind of gets carried over here. So when we talk about the actual connection between 2 nodes, we'll call that an edge. And for the purpose of a tree, we'll think of that as a unidirectional edge. So we'll only travel in one direction, kind of starting at the root and going down. Now, that's obviously, you can imagine that we're we aren't really limited to that, right? We could start to connect things where we could travel in both directions. And we could connect things not just in a strict hierarchy, and that's where we get to more of a graph. So a tree, I believe, is technically defined as a singly rooted acyclic graph. We won't have to know that, but, or singly rooted directed acyclic graph, yeah. So all it means is that it doesn't, it's a graph that only has one root, you go in one direction, and you never cycle. So that's important for a tree. Like if you start at a node and you start moving down, you will never end up back above yourself where you started. So just a visual example of a tree. You always have this one root node, and we typically draw the trees in this orientation with the root at the top and then branching downward. You could probably flip it if you wanted to. This is just how it's commonly drawn. And you can see these edges that connect these are directed edges. So you've got arrows indicating from the nodes to the children. So more terminology, and thankfully this terminology is pretty straightforward. So we describe it kind of similar to like genealogy terms usually. So we have parents, we have children, you can have just generally ancestors or descendants. So, anyone above you in the tree is an ancestor, and it doesn't matter how far above they are, anyone below, descendant. And then we've discussed, so you just saw that, you have the parent nodes and the children nodes, and you have the links between them. And so that is the most basic, structure of the tree. It's very straightforward. There are a few other things. So obviously we have a root node that starts our tree. We have what sometimes we call it branches, but it's probably a little bit more intuitive to think of them as internal nodes. It just means that they're not, it means that they both have a parent and a child, at least one of each. So they're within the structure. And so you'll see that called either a branch or an internal node. And then we have leaves. And so leaves are the nodes that are kind of at the bottom when we draw it that way, and they have no children, nothing connected to, so they just have a parent. So looking at this example, we can look at these nodes, and so if we look at N7, we can see that its parent is N3, and that it also shares that parent. So N8 also has that parent. And so in these two nodes, because they're at the same level with the same parent, could be considered sibling nodes. You may see that kind of description of them. So they're still all descendants of N3. They're also N7 and N8 are also descendants of N1. And they are ancestors of, in this case, NB here. And let's see. So N1 and N3 are ancestors of, N7 and N8, right? There's both of those. And so, if you wanted to extend that, you could say, what are the ancestors of N9?
4, 2, and 1.
Yeah, N4, N2, and N1. And so it is important to note, so for the ancestors, right, you have to be able to follow this edge. So N5 would not be an ancestor of N9 because it's not on that path. All right. So we've got our root node, N1, typically drawn at the top. And it is the only node in this structure that does not have a parent of its own. Here are the leaves in green, and very green. So these are all of the nodes, as we mentioned, that do not have any descendants or any children or anything. They're kind of just out here on the edges. And then here are the branches. So kind of in this purplish color here. And so you can see they have both. They both have a parent, and then they have some descendants connected to them. And of course, those are also called internal nodes. And I do think that's a little more intuitive than a branch, because you remember that we call these edges. Okay, so there are some other terms that we can use when we talk about this. So we've got this structure, we've got some general ideas about how to talk about the nodes in relation to each other. So then these are kind of based in mathematics. So this is, like a lot of things, this comes before like computer science. Before we were using this as programming, these concepts existed. So the concept of a degree. So every node has a degree, and all the degree is the number of children that node has. So there's also the idea of a depth, which is pretty intuitive when you draw out the tree, kind of in that way. And so that's the number of edges that are between the root node at the top and a specific node. And so when you look at the drawing, you can see, you're coming down a level each time, and kind of getting that depth. So obviously the root node itself has a depth of 0, because at the top there are no edges before it. All right. Let's see. And so should have made that yellow. But you'll also see that, like, when we talk about depth, so we'll call them levels. And again, when we draw that out, like, you'll just kind of say, okay, this is level 0, level 1, level 2. And so then you can also say, which nodes are all on the same level, regardless of, who their ancestors are or whatever. So another thing that we use, the height of a node. So it's the largest number of edges along any path from the node to a descendant. The height of a tree is the height of the root. So it's basically saying how deep does this tree go in the most extreme case. So if we're doing levels, it's going to be like the level that's the highest number, but the furthest down in our drawing. Okay, so degree, if you remember, is the number of children that the node possesses. So n2, what's the degree of n2? 3, yes. So it has children n4, n5, n6, and just important to remember, it is only the direct children that are connected to this node. So we don't keep going any further in this case. All right, how about n8? Yeah, no children. So it's a leaf. It's just out here. Nothing below it. All right, so the depth of the node, the number of edges between the root and the node itself. So depth of n4. Yes, 2. So get this edge here and then this edge here.
And what was the first? This is asking about the depth, but at first it's asking about the degree.
The degree, yeah. So yeah, and the degree being like the number of children it has. Yeah. Okay, how about n1, the depth of n1? 0, yeah. So that's all I want to talk about today on trees. On Friday, we will start to get into the more technical part of this and how we write code about this and what we want to do with this. I think trees are kind of enjoyable and not that bad. Like, it's one of the more fun data structures. So hopefully you will find it that way too. But we will talk more in detail on Friday. Please remember to do your challenge things and let me know if you need anything. I will post code about that see out part. Yes.